Hi, my name is Sebastian Döpke. I'm the head of Simcenter3D and software development at CAE Innovative Engineering. Today, I'm going to demonstrate you two of our tools, Durability Inspector for FKM assessment and the Submodel Inspector to perform a submodel. And today's video is just a quick introduction into the topic. If you are interested in more details in these tools, please contact me anytime. So our tools were developed as part of the Simcenter3D environment. We built them on top of this environment, so they can be used in collaboration with the pre and post processing of Simcenter3D. So while you are creating your finite element model, simulating structures with linear elastic or nonlinear analysis, you can use these tools on top of this environment. So one of our tools that I'm presenting today is the Durability Inspector. To perform FKM assessment, we have additional topics or tools, Bolt Inspector for the evaluation of threaded bolts, Spindle Inspector for rotating systems, Weld Inspector for weld lines, in particular on shell structures. And the second topic for today is the Submodel Inspector to perform automatic submodel approaches. And these tools work together very well in combination because often for the FKM assessment and in particular the not stress approach, you will need a very fine and smooth distribution of the stresses, and therefore the submodel routine is a perfect combination of these two tools, FKM and submodel approach. And I want to demonstrate today this topic on a model. It's a carrier, as a large structure carrier for a tractor. And in this case, we have two load cases or three load cases, a pretension load case, and then additional moving loads for this part. And we will see on the stress level of this part that we need some finer mesh representation. This is a typical example because it contains a long simulation run. So this model solves about 24 hours with different load cases. Model size is about 3 million degrees of freedom. So a quite large model. I don't want to solve this here again, so I will load an already performed simulation, and we can see, so there are additional 1D elements where the part is fixed, and then we have gravity loads, pressure loads, and forces acting on the structure. If we look at the stresses and scale or limit our stresses to 200 megapascal, so this is a S235 material, we can see that we have a peak location in this region. And if we go into further details, we can clearly see that although the mesh, I will enable the mesh, we have at least 2 or 3 elements over this blend, but you can see that the stresses jump between the individual elements. So these are too high stress gradients for an FKM assessment. We can't clearly say where the peak location would be and which value it would have. So as an example, here I am measuring a value of 190, and in the next elements, in the next element 176, and the next just 93. So there's a huge stress gradient between these elements in this particular region. And to evaluate this anyways with the FKM approach, we can use the submodel approach as in a first step and create a submodel out of it. And then in a second approach, we will do the FKM assessment on this particular submodel. And let's do this. So I'm jumping back to the global model, and the submodel inspector is a toolbar that we offer with a workflow that you can perform, and I'm going to go through it very quick. We generate the submodel out of it. All this is supported by our tool. So we offer functionalities to generate the model, to perform Boolean operations, to mesh the parts automatically. And we will be asked which parts we want to take for our submodel routine. So I'm going to choose the large casing part. And it will create the underlying assembly. It will also save all the parts in an individual folder so that we can later on inspect the individual submodels independent from the global model. Wavelink was created, and then we have options to perform the Boolean operation either with a block or a sphere. So I will choose a block in this case, and with the Boolean operation, we will create this submodel. The boundary faces were already created where the constraints will be applied to and then we perform an interpolation to apply the constraints from the global model to the submodel. There are some details in the structure that I want to neglect, and then we can with that switch to generate the CE parts. As we do that, we will get the material that is defined and was created in the global model, extract that and also apply it to the submodel. So this is a process that you currently are seeing where where it loops through the assembly fam and then identifies all materials that were created. And we just have then to select the proper one in the submodel. So this process is already done. You can see that meshing operations are performed. So we do an automatic meshing. We are going to be asked to select a material. So you can see material was also imported. We just move the mesh to the correct one. And then we can do some mesh refinement. We want to have a smooth distribution of the stresses in that region. So we will apply a seed mesh on the structure. Okay, and we have a very fine mesh in that region, maybe already too fine, but we will see. And with that, we will jump into our simulation. Next step is the mapping of the constraints. We have a routine for that. That's extracting the displacement from the global solution. In this case, we work with two solutions from the global model and create a solution 101. And it will then extract the displacements from the global model and map it to the boundary of the submodel. And when we inspect the stresses later, we can see that this is sufficient to represent the system of equations or the loading conditions, and we will find a very smooth distribution of the stresses in this region. So the mapping was performed. We see two individual subcases that were created, and we can solve this model. It won't take too long. That's the main benefit of the submodeling approach, because in the global model, what you would need to do is refine this region and then solve the whole model again. It would again take at least 24 hours. But in this case, because we are just computing a subset of that global model, we can reduce the simulation time drastically. So we are computing two load cases here. And let's see how long it would take. I would estimate about a minute. So this was the first subcase. We can see about 300,000 degrees of freedom. And this is the second subcase that we compute here. And the solution is done. And we can inspect the stresses and displacements. So these are the displacements. We can also plot the displacement in a split screen mode, so that we can inspect the global model and the submodel at the same time. So here we have the displacements of the model. I will highlight or hide the mesh. And when we switch to the stresses, we will see, so I'm going to choose the stress results for this model and for the other one as well. And then reduce the maximum legend to 200. And we can clearly see that the stresses are much better represented. Even if we choose a banded contour style, we can see on the left very coarse distribution and on the right a very smooth distribution, and we can clearly identify the maximum stress location and can be sure that we capture the maximum stress effect. We also have options to measure the stresses. So if I switch back to the submodel, we can inspect the stress quality with a quality measurement, and for FKM assessment, stresses should be below the region of 10%. So if you perform this evaluation, we will see that we have a deviation of 27%, but only on the boundaries a group will be created, and this region has a maximum stress gradient of 27%, but in this region all stresses are below 10%. So that's fine for an FKM assessment. And this would be our second step. So now we're switching to our second tool, evaluate the submodel with the durability inspector. It is also embedded in Simcenter3D as a toolbar. We switch now to the durability inspector toolbar and perform an FKM assessment based on this submodel. And now the durability inspector is loading up, where we assign material the type of FKM assessment we want to perform. So it's reading the model, and we are loading the two results that we have here, or two subcases. We will have an pulsating load, or maybe an alternating load between the two. This is handled by the durability inspector automatically to calculate mean stress and amplitude based on these two subcases. And we will perform the FKM assessment, static and cyclic degree of utilization. We can implement all the design factors, choose the material, it's already set here, define consequences of the safety factors and so on, and define what limit of or number of cycles we want to compute. In this case, this is set correctly, and then we can perform the FKM assessment. Okay, it says ready, so the evaluation was already done, and we can plot these contours now. Let's see, we have here the output static degree of utilization, or dynamic degree, or maximum cyclic degree of utilization. And we should then limit the legend now to 1, because this would represent 100% degree of utilization. And we can see in this region, which we want to evaluate, is it's below 100% clearly. And we can perform this type of analysis on particular any part, and especially for large structures that would take a long computational time, or where the global model does not represent a structure or a welding very well. So this was a quick demonstration of our two tools. If you have more questions, please contact me.